right now is going to be not HIPAA, sorry. It's going to be 5.1 and 5.2 in the book. Now this is actually completely new. So we did not talk about this last year, at least in my class. Might not be completely new for you, but it's going to be new for everybody else. I'm talking to people who are here, those of you who are watching the video. So this is about energy, okay? Now we haven't talked a lot about the way, we've really focused on matter a lot more last year, how matter interacts, how it rearranges in a chemical reaction. We didn't really deal a lot with how energy is involved in the process, okay? And so that's really what this chapter is about. It's kind of an introduction to thermochemistry. We're not going to get into like entropy or anything like that, if you guys have covered that in your physics classes at this point. And even when we get to entropy, it's covered in a lot more detail in your physics class than it will be in here. You may not even be happy with the way that we talk about it in here. I know some of the physics people have been in the past. They're like, well, that's way too sloppy, the way you're dealing with entropy. But anyway, we will talk about all those things, but for right now, we're just talking about energy, okay? So energy, you guys know the definition for energy? Oh, yeah, you're looking in the book, right? Did you know that before?
Yeah.
Yeah. So there's kind of really two things that we think about in chemistry. Can it produce work? Or sorry, can it do work? Can it produce heat? Okay. Now, this one is probably going to be more familiar to us as far as
reminder,
chemistry.
is in the cafeteria.
Boy, that's on video. Right. So, as far as chemistry is concerned, the chemistry we've done so far, it's easy to think about heat changes that occur in those processes, right? The work part, that may be a little bit harder. What's an example of maybe chemical energy being used to do work? Okay, a rocket, right? So you've got a lot of combustion going on there, and it is actually propelling that rocket. It's moving it, okay, with a force up into space. And I don't know if you remember this about work, but work is, I say remember, you may not even know this at all if you haven't taken physics in high school. Force times distance, okay? So it's a certain force applied over a certain distance, okay? If you don't move something, work is not considered to be done in the technical definition of work. So I could push on this table all day, but if I don't move it, I haven't done any work, right? Even though I may be exhausted. So that's the work part of that definition, okay? Now let me see if it talks about it in these two sections. It does, okay? So really what we end up getting to here is ultimately an equation that looks like this. Change in energy is equal to Q plus W, okay? W stands for work. Q, don't ask me why, stands for heat, all right? So basically, if we're trying to figure out the change in the internal energy of something, then if we know the heat change and the work change associated with it, then that kind of sums up the energy change that takes place in that particular object, okay? What else do we cover here? That I guess a couple other equations, and again, this gets real physicsy for just a little while. That's a word, right? Physicsy. Go full screen here. But then we get back into the chemistry fairly quickly in 5.3 and 5.4. But another couple equations that you might want to know here. The equation for, you guys remember the difference between kinetic and potential energy? Okay. So kinetic energy is the energy of motion, right? Okay, so kinetic energy, you have things that are moving, right? Potential energy is maybe a little bit harder to define, but what is potential energy? Yeah, stored energy is probably the best way to say it. Has the potential for movement, something like that, okay? Stored energy is a good way to put it. I like that especially when we're talking about chemical potential energy. Okay? When we're talking about chemical potential energy, it's the energy that could be released when a bond forms, or the amount of energy it takes to break a bond, that sort of thing. Okay? So electrostatic potential energy is a very specific form of potential energy that is really, really important in chemistry. In fact, this is essentially chemistry. There's not a lot in chemistry that doesn't involve electrostatic. Now, you do have electromagnetism as well. Well, I guess electrostatic could be put under the overarching category of electromagnetic. Okay? So if you talk about electromagnetism in general, that is chemistry. Okay? We don't really deal with gravity. In this class, we don't deal a lot with the strong or the weak nuclear forces. That's more for... See, I wish we were still doing nuclear, but we don't anymore. Okay? But electrostatic energy, do you guys remember the equation that talks about electrostatic potential energy? It's Coulomb's law. All right? And I've mentioned this before. So Coulomb's law, the energy is equal to, is it a constant? Yeah, it's constant first. Q1, Q2. Now, sometimes these are written as lowercase q's as well. I don't think it matters that much. Over the distance. I think it's just distance. Yeah. Okay? So that's Coulomb's law. Q1 times Q2 over D. All right? And all that means is these stand for charge, right? Q1 and Q2 are just the charge on those particular, maybe it's an electron, maybe it's a proton, those sorts of things, okay? And then the D is just the distance in between them, all right? So that will tell you the amount of attraction or repulsion you have between them. If it's two electrons, since they have the same charge, they're repelling each other with this amount of energy, right? If it's a electron and a proton, positive and a negative charge, then they're attracted to one another with this much energy, okay? So that's kind of the idea there. Does that make sense? Like I said, we've talked about Coulomb's law a lot before. This is going to become really, really important when we start talking about ionization energy, why things interact with why certain atoms interact with other atoms the way that they do. We're going to go into a little more detail about that this year. We talked about the periodic trends last year, but we're going to hit on that a little bit harder next. Well, no, it's still this semester, I guess. Okay. The other equation that might be slightly useful, I don't know. I mean, I don't know if they even include this on the formula sheet anymore, but they used to, the formula for kinetic energy is 1/2 mv squared. And all that's showing you is that mass and velocity are both, those are the things that determine an object's kinetic energy. So the bigger the object is, the more kinetic energy it has. The faster it's moving, the bigger its kinetic energy, okay? I mean, the way I always think about this is envisioning something hitting me, right? If I want to have something hitting me, I want it to have as little kinetic energy as possible, right? So I would prefer for it to have a small mass and a low velocity, right? Because that's going to mean that it will hurt less when it hits me because it has less kinetic energy. What else should we talk about? You guys know the unit for energy? The SI unit for energy is the joule. Did we talk about that last year? Did we? Oh, okay. Oh, we talked about it in the context of when we did the electron jumping from one energy level to another, didn't we? Yeah, I forgot about that. Good. The other one is the calorie, okay? Joule or calorie, these are the units for energy that we usually deal with. Typically, it's going to be the joule in here, but it's when we get to calorimetry, actually, we'll use the calorie. Calorimetry, calorie. Guess you should use that unit since it's in the name. The other big idea from 5.1 is the difference between system and surroundings. I don't think we talked about that last year, did we? Okay. So you've got a beaker. A reaction is happening inside the beaker. That's your system. Okay? The surroundings is everything else in the universe. All right? Now you get to decide what your system is. I could actually decide that the entire universe is my system, which makes this the surroundings, the beaker. Okay? You get to define what your system and your surroundings are. Okay? So, sorry, hang on just one second. Let me pause this. All right. So, let me get back to full screen here. So again, system is whatever you define it to be. Surroundings is everything else. Okay? In the entire universe. So that's not that complicated of a concept. Now the reason we talk about this is because usually in a chemical process there's an exchange of energy between the two, right? So either if you have what's called an exothermic reaction, then the energy flows out of the system to the surroundings, and the surroundings get warmer. Okay? Or you can have an endothermic reaction where the energy goes from the surroundings to the system, and the surroundings get cooler. Okay? And so that's, you can kind of figure out, you can determine what's happening there based on the temperature change of the surroundings. Okay? So that's an important concept to know. Talked about internal energy already. And we just talked about endothermic and exothermic. So this right here is an exothermic process, and this is an endothermic process. Exothermic means the heat is going out, right, out of the system. Exo, exiting. Endo, into the system. Okay. State functions, they kind of told us not to worry about that this year. So you don't need to. I don't think you need to worry too much about a state function as far as like the definition of it. So other than that, that's about all that you're going to really need to know from 5.1 and 5.2, I think, are those concepts. Let me look at the practice problems that are here. See, this sample exercise 5.1 is not all that critical. I'm not going to give you a sample exercise like that. 5.2 is a good sample exercise because it talks about determining delta E if you are given information about the heat and the work. So let's see, how much time do we have? I said I was going to go to 2:45, is that right? Or 2:50, okay. So we've got a little bit of time here. So let me, well, why am I doing that? I don't know. I want to stay on that screen. Okay, so we're going to look at the sample exercise 5.2. It's on 171. So it says two gases, A and B, are confined in a cylinder and piston arrangement, like in figure 5.3. They react to form a solid product. A plus B yields C. As the reaction occurs, the system loses 1150 joules of heat to the surroundings. The piston moves downward as the gases react to form a solid. As the volume of gas decreases under the constant pressure of the atmosphere, the surroundings do 480 joules of work on the system. What is the change in the internal energy of the system? Okay, so this is where you're going to need this equation right here. Delta E equals Q plus W. Okay? And this is kind of an important equation for you to know for these first couple of sections here. All right? So looking at that example.
Glenda, can you contact Donna in the main office, please? Glenda, contact the main office.
Okay. As we look at that example, what is the, sorry, you guys on the right page here, 171 at the very bottom, sample exercise 5.2. Okay? What's the heat change in this one? Just reading the problem here. You see it? Loses 1150. Okay, So it loses 1,150 joules of heat to the surroundings, all right? Now, the way that we're going to define that, and it's important, in this equation, you need to understand the signs that are used when something changes. And actually, table 5.1 right above that sample problem is a useful little summary here of when Q would be positive, when Q would be negative, okay? So because the system is losing heat here to the surroundings, what sign do we need for our heat? It needs to be negative, right? Okay? So for figuring out this delta E here, this is negative 1,150 joules, okay? And then we're going to add that to our W, which is our work, okay? Now how much work is being done here? Okay, 480 joules of work on the system, not by the system, right? Okay, so that energy is actually being added to the system by the surroundings, okay? So if it's being done on the system, our W is positive, okay? So negative 1,150 plus 480 is going to give us our overall change in energy of the system, okay? Now it's important to note, this is the energy change of the system, okay? So negative 1,150 plus 480, I'm going to cheat and look on the next page, negative 670 joules. I really probably could have done that in my head, but so there is your delta E, okay? Which you kind of need to understand what this is telling you. If this is negative in terms of the system, that means energy is flowing out of the system. Overall, there's a change of energy so that the energy is going from the system to the surroundings, okay? So it's important to understand, once you get done with these, what the negative or the positive sign is showing you at the end, okay? And that's kind of the idea here. Yeah, I mean, that's pretty simple, right? Not that bad, and there's really no other sample problems in 5.1 or 5.2. So I think probably that'll be enough to get you guys set for some of the practice problems we're going to do in class tomorrow, okay? And actually, I think we're going to do a little activity in class tomorrow. So that's another thing that I'm hoping here, is that because I'm covering this stuff outside of class a little bit more with these videos, that we'll have a little bit more time in class to actually do the practice problems, because we haven't had a lot of time to do that so far, okay? All right, so I think that's pretty much it for today. Not a lot to cover there because it's really just the basic introductory stuff. All right, see you guys in class tomorrow.